This is a Q-2C target drone, ground-launched from a zero-length rail. It is also air-launched from a GC-130 aircraft. It has performed reliably at altitudes up to 59,800 feet. Developed for the U.S. Air Force by the Ryan Aeronautical Company, this drone is now in use by all three branches of the Department of Defense. The mission of the Q-2C is to furnish economical, high-speed target service. The Air Force awarded a contract to Ryan for feasibility and systems integration studies, scale model radar reflectivity tests, and a flight demonstration program on Q-2C drones. Radiation Incorporated, under subcontract, conducted scale model tests. These tests indicated that the effective radar echo area of the Q-2C drone could be reduced significantly by the installation of a screen across the engine air inlet and by blanketing the sides of the fuselage were checked for satisfactory performance. By this time also, the drone radar had been set up near the beach at Cape Canaveral and had been calibrated as required for final phase guidance control. After 2 years of development sponsored by the Ryan Aeronautical Company, the United States Air Force, in February 1962, contracted for the manufacture and flight testing of a special drone reconnaissance system. Using the basic design of the Q-2C target drone, the Model 147 evolved into various configurations. The 147A, used for early flight testing, was a standard Q-2C drone with a modified nose section which accommodated the photographic package. The fuselage was lengthened 35 inches to accommodate additional fuel. The basic 147 model was flight tested during April and May 1962. The 147C and 147D models are essentially the same as the Model 147A, with some internal changes. Lightning bug drones have been on operational status with the United States Air Force since July 1962. The photographic system consists of the Hicon Model 233 camera with image motion compensation, an oblique servo amplifier, signal integrator, window assembly, and heating blankets. Operation of the system is controlled by the programmer. From 60,000 feet altitude, a strip 300 miles long and 20 miles wide can be photographed. The 147D version, with associated equipment, provides a special capability in the area of electronic reconnaissance and surface-to-air defensive armament information. All electronic signals received by the drone are converted to video or CW level signals and transmitted to R-47 aircraft and appropriately positioned surface stations equipped to receive, assess, and record this information. If defensive weapons are fired, the radar guidance and fusing signals received by the drone are converted and transmitted. An explosion in close proximity to the drone would be within the field of view of the optical tracking equipment, and the detonation characteristics and location relative to the drone are observed and recorded by the surface optical tracking stations. Overpressures created by the explosion are measured by pressure-sensing devices on the drone and transmitted to the R-47 aircraft. Miss distance in range and azimuth from the drone can be determined from this information. Improvements to increase the navigational accuracy, operational ceiling, and range were added to the 147 model, resulting in the new Model 147B configuration. Major changes were the addition of a Doppler navigation system and a new, larger, swept-back tapered wing. The Ryan Model 523 Doppler Navigator is a two-beam continuous wave system. The outputs consist of a distance pulse emitted in 7-mile increments and drift angle. The distance pulse advances the programmer, which has been set to change the drone heading at specific mileage increments. The drift angle modifies the output of the heading reference to give the desired ground track. B was launched on the 3rd of May, 1963. Launching of the 147B proved to be normal in every respect. Because of the high altitude and increased range capability of the Model 147B drone, it was not possible to utilize chase aircraft to satisfy range safety requirements. It was therefore necessary to provide ground stations capable of tracking, control, and data acquisition. The max, totaling over 60 hours, the 147B model has met or exceeded all requirements. The overall theodolite and tracking cameras were used to obtain recovery trajectory data and rate of descent data on both the drag and main parachutes. A new 100-foot tri-conical chute improved recovery, and over 80% of the flights resulted in only minor damage to the drone. On the facility of an RB-57F aircraft as a test platform, made possible for the first time a controlled test program under operational environments. With the system operator on board, test parameters could be varied in flight to achieve maximum test effectiveness. In this following film sequence, observe the right outboard contrail as it is being suppressed. Nine test missions were flown, 6 in the neighborhood of the Panama Canal Zone. This area was selected for its high altitude, severe low temperature environment, which closely duplicates that of the overseas operating area. In the flight test sequences, agent was initially injected at a high flow rate. Then the flow rate was decreased until the contrail reappeared. In this manner, the minimum agent flow rate required for suppression was determined. As this sequence continues, you may observe the contrail reappear. The molded foam subassembly, contoured to fit the wing fillet cavity, is installed with no modification to the vehicle. The wing fillet provides the necessary structural support. The optimized contrail suppression system was demonstrated over the White Sands Missile Range, New Mexico. 2 flight tests were conducted. A U-2 aircraft flew chase. When the system was activated, the contrail from the 147 was suppressed. From the ground photographic film, you can see the RB-57F photoplane and its contrails on the left. On the right is the contrail produced by the U-2 chase aircraft. The U-2 is barely visible. In the center screen, leaving no contrail, is the white 147G aircraft. The system performed as intended and satisfied all its design objectives. By a series of efforts, a contrail suppression system has been developed for the Model 147G Special Purpose Aircraft. An optimized production model contrail suppression system was demonstrated in flight on board a Model 147G Special Purpose aircraft. This film presents a summary of the efforts leading to the development of that system.